Okay, so what is show something. So it's a pleasure to have a friend here, Pasquale Blasi. Pasquale is a full professor. I had my notes, but somewhere. So I will. Pasquale is a full professor at GSSI in L'Aquila. He obtained the PhD in 1997 in L'Aquila with Berezinski. Berezinski was the Pope of cosmic ray physics. And then he moved to US in Chicago at the university for 2 years and the Fermi Lab for other 2 years. Then he came back in Italy, in Arcetri at INAF for many years, is where he did most of his career. And since 2017, he's full professor at GSSI. He also served as director of the physics department at GSSI. So Pasquale is a guru of really is a pope of cosmic ray physics and astrophysics, high energy astrophysics. He published more than 200 papers. Some of them are really seminal papers in the field of cosmic ray acceleration and propagation. He was one of the father of the nonlinear shock acceleration, particle acceleration at shocks, with pioneer really studies about the feedback of cosmic ray acceleration at shock in supernova. He also is interested in many fields of astrophysics, from galactic to extragalactic. And in 2003, I guess, he obtained the Shakti Rugal Award from the cosmic ray community due to his important studies in cosmic rays. He was invited and review speaker in 100 plus conferences and so on, and he is also involved in several big experiments, including the CTA and the Fermi Lab. So today, Pasquale is going to talk about, obviously, particle energization, astrophysics, and the origin of very high energy cosmic rays. So, and you will trade the session. Thank you, Pasquale.
Thank you. Thanks for the great introduction. Although being an atheist, it's funny to be labeled as a anything. Okay, so the topic of the talk is, in general, particle energization in astrophysics. And I sort of wanted to emphasize the origin of very high energy cosmic rays, because really the problem of energization of particles in the universe is ubiquitous. Whether you actually look at supernovae or you look... Right, that's a good point. So whether you look at supernova remnants or the sun of microquasars or AGN or clusters of galaxies, starbursts, in all these sources, you actually see no thermal radiation. Therefore, you need to make up some way to take particles from the thermal plasma and push them up in energy. This is a tremendously challenging effort in astrophysics. It's also, of course, a tremendously challenging effort on Earth. We built LHC to accelerate the particles, but in a sense, let me say that it is a little bit harder to figure out why in the universe it is a bigger challenge. And I'll spend a few minutes trying to discuss this point, again, this one. So most of the universe, really all of it, I would say, is in a stage of plasma. A plasma is basically a system of electrons and protons, usually in thermal balance, with an extremely high electrical conductivity. You know that when that happens, if you try to apply an electric field, particles move with respect to each other and short circuit the electric field. As a result, you have no electric field, right? And yet, in order to change the energy, not the momentum direction, but in order to change the momentum magnitude, you need an electric field. There is no other way that we know in nature, and actually that's exactly what LHC does. The particle is injected in a loop, but the particle energy changes only when it crosses selected places where the electric field is present. You need an electric field to change the energy of the particle. And in the universe, you cannot have a net electric field. There is only one electric field that you can possibly not short circuit, which is the induced electric field. In other words, you are sitting in a plasma in which there is no electric field, but there is a magnetic field. Those are pretty common. Then you take this plasma and you set it in motion. In another reference frame, you will see the magnetic field in motion as a net magnetic plus electric field. So the question is, can you change the energy of the particles using that induced electric field? So a necessary but not sufficient condition in order to accelerate particles is to have magnetized plasmas, and you want them to move as fast as possible because the electric field is V/C times magnetic. So if V is very far from C, you have a small electric field. The closer you are to relativistic, the larger is the electric field in principle. So it's a necessary, but it's not a sufficient condition for particle acceleration. Thank you. For particle acceleration to take place. So very few small, simple arguments here. So I don't think that. Okay, thank you. So the momentum of the particle changes because of this induced electric field V/C times B, and V is the motion of the plasma itself, not the particle, right? So the energy of the particle changes roughly of this amount in time. And if you take the time as R, the size of the system, divided by the velocity of the plasma, you can estimate what's the maximum energy that you can possibly reach. This is an absolute upper limit. It doesn't mean that really in an astrophysical source you get that, but that's an order of magnitude of the highest possible energy that you can think of. And now you can play around a little bit, just square these two quantities and divide by the suitable numbers, you get this stuff here. And I wanted to isolate B squared over 4 pi on the right-hand side. This is the magnetic field, which is present in the system. And you can estimate the point in flux luminosity, which is B squared over 4 pi times the surface of the source times beta c, where beta again is the velocity in units of the speed of light, is the velocity of the source, is the velocity of the plasma. And of course, this Poynting flux luminosity must be smaller than the total luminosity of the source, right? But by definition. And so all of a sudden, look how beautiful, you get an absolute upper limit to the energy that you can, in your wildest dreams, accelerate in that plasma, which is proportional to the square root of the luminosity of the source. This is, it goes by different names. Somebody calls this the Hillis criterion. It's a variation of it. But basically it gives you a connection between the highest value of the maximum energy that you can possibly reach in an accelerator as a function of the luminosity of the source. And it's supposed to tell you, look, if you want to reach high energy, you better get a very luminous object, very energetic source. That's why we look at the most energetic things that we have at our hand if we want to have to reach an energy which is on some energy range, right? So for instance, if you're interested in PeV, well, you need of the order of 10 to 37 Hertz per second or so, and then you're there. Well, you're there in terms of the highest possible value. Then you need somehow to implement all this in nature. Namely, you need to deal with the complexity of the system. And usually the maximum energy that you actually get in an accelerator is way smaller than that, okay? So this is an absolute upper limit. I also want to point out a couple of things which are often probably not as obvious. When you talk about accelerating particles, you have many degrees, many layers of problems that you have to deal with. One is known as the injection problem. In other words, you have air in this room, you push it up in temperature, you get a plasma eventually, but then what? Then you have a bunch of electrons and protons, and there is no reason whatsoever why one of these protons should get non-thermal, and the others, 99.9% of them, would stay thermal. So how does nature decide that actually one of the protons in your plasma should be promoted to be a cosmic ray, to be a non-thermal particles? The other point that I want to make is that, and we will discuss this later on, is that in many of these acceleration processes, the phenomenon of energization, of particle acceleration, actually works only when the particles change the environment in which they're moving very considerably. In a sense, it's a sort of a nonlinear back reaction between the accelerated particles and the plasma, which is essential for particle acceleration to take place. And I will try to discuss this a little bit more later on. Now, there is a sort of short circuit between what people call cosmic rays and accelerated particles. I showed you many pictures of the sun, supernova remnants, and so on, all of them showing non-thermal activity. And of course, most of the particles that are producing that radiation will never reach you, okay? But still, they are there, and they behave exactly like the cosmic rays that we detect at the Earth. So traditionally speaking, when these particles are considered in the realm of their own source, we call them non-thermal particles, non-thermal particles or accelerated particles. When they reach the Earth, we call them cosmic rays, but you understand that it is a stupid distinction, right? We're talking about the same physics. Yet, of course, we live on Earth, and so that's what the cosmic rays that we reach us look like. And what is that? So it is a sort of a power law looking kind of thing with a flux that drops dramatically in the range around here, 10 GeV or so. We have a particle of about 1 particle per meter square per second. And at the energy around the knee here is meter square per year. Down here is 1 particle per kilometer square per year. And at the very bottom here, the so-called GZK feature, we're talking about particle flux of 1 per kilometer square per second. And that means, of course, that in order to detect that thing, that flux, you need to build extremely large telescope or live a lot of time, but that's not very practical. The spectrum overall, what I mean by overall or all particle means that I don't care what I'm seeing. I just sum everything together. Protons, helium, carbon, everything shows a feature around a million GeV, a couple of million GeV, which is the knee in the spectrum. And then there is some feature that we call the ankle, which is supposed to be something, hardening like here. It's less visible here, but there is also a broken angle or a second knee around 10 to 17 electron volts here. And I wanted to spend a little bit of time talking about these things, but keep in mind that the last 10 years or so have been dramatically, I've seen a dramatic improvement in these observations, because now we actually see the individual components that make up this spectrum of the cosmic rays. So we see protons, helium, carbon, and so on and so forth. And we even see the secondary nuclei, which derive from a nucleus broken while moving in the environment. And those secondary nuclei contain a lot of information, how long the cosmic rays spend inside our galaxy. So the amount of information that we have is now incredibly larger. Just a couple of days ago, this result came out from the DAMPE collaboration, in which you see the spectra of protons up here, helium, carbon, oxygen, iron. And one thing that, independent of the labeling, that you should be very impressed by is the fact that there are features in these spectra, so they don't look at all like power laws. And when there is, as you know, a power law does not contain any physical scale, either in energy or in anything. But when you see a broken power law, usually saying that something is happening there of physical type, right? So a change in regime. But the second thing that you should be impressed by is that all of these features are dependent only on one quantity, on rigidity of the particle, which is the energy divided by the charge. So once you correct for the fact that the helium is twice as charged as proton, that carbon is 6 times the charge of the proton, and so on and so forth, all these features seem to align pretty nicely, and all these features seem to align pretty nicely in rigidity. The first feature occurs at roughly 300, 400 gigavolt in rigidity, and the second one is about 20 teravolts in rigidity, okay? So far, so good. Now, of course, we have to deal with what that means. What is that we are seeing here, okay? So I wanted to focus a little bit on the main component of the cosmic waves, the protons. And you see that the proton spectrum is now measured from 10 to minus 6 PeV, so 1 GeV, up here to 10 PeV. And, well, there are several features, again, that pop up. This is the same hardening I showed before at 300, 400 gigavolts. And this is the same feature I showed you before at 20 TeV, but it doesn't finish there. It picks up again. And eventually, at the knee, the protons show a knee structure. What does that imply? Well, it means that the knee, which is a feature in the all-particle spectrum, seems to be actually caused by the protons themselves. Okay, so without even thinking too much, then you would expect that helium should get to an energy twice as large. You remember rigidity. Carbon should get 6 times higher, and so on and so forth. And you see here helium, which is also a factor of 2, and it has a similar structure. This was unthinkable just a few years ago. And finally, we see this structure in the lasso data, which I think is really unbelievable. Okay, so this is unbelievable, but still, it doesn't address any physical issue. Where are all these things produced, accelerated? And is it a challenge for us or not? Well, there are many interesting aspects here that each one of them is probably a separate colloquium of 1 hour, but we don't have that. So I will try to focus on one of them, on the acceleration of particles. Now, you might have, I'm sure you did hear, you might have heard about the fact that for 50, 60 years now, people are talking about the so-called supernova remnant paradigm, namely that the bulk of the cosmic rays that we see at the Earth might be accelerated in supernova. Of course, it was not pulled out of the magic hat. It's just a little bit of numbers. If you accept of converting of the order of 3 to 10% of the bulk energy of a supernova explosion, which occurs typically every 30, 100 years or so in the galaxy, into cosmic rays, then you can easily account for the global energetics, right? So it means that if you're able to convert a relatively large efficiency, right? 10% is not a small amount. 10% of the bulk motion of the shaft associated to a supernova remnant into cosmic rays, energetic seems to be okay. Moreover, we observe non-thermal radiation from the source itself in the radio, in the X-rays, in the gamma rays now. So we know that these sources are accelerators of cosmic rays. What we don't know is up to which energy they can, all these statements remain true. Namely, up to which energy we can consider supernovae as the main sources of the galactic cosmic rays. In particular, in 2004, about 20 years ago, people started measuring X-rays, very thin structures, very thin filaments in these supernovae. And the thin filaments are associated with synchron emission from high energy electrons. The fact that they are so thin means that the electrons are losing energy inside the filament. So the field there could be inferred from the thickness itself, and you get a tremendous number. It's of the order of hundreds of microgauss, in some cases milligauss. But the field on the other side, in the upstream of the shock, in the ISM, is only 2-3 micrograms. So clearly something has happened in that very small region, and people had expected something like this for many years in terms of an effect associated with cosmic rays themselves. It's the particles that produce magnetic fields through channels that I'll try to describe without going too much into detail. So these are the obvious reasons why focusing on supernova remnants. The negative side of it is that we have never seen a supernova remnant accelerating particles to a PeV. There is not a single instance of a supernova accelerating to PeV energies. And there is no evidence for acceleration of particles maybe accelerated in the past and leaving these sources. So emission from around the supernova remnant. I will discuss one case in more detail. So what's the situation? Should we keep focusing on these sources or not? Well, let's look at it. So this is the gamma ray observations from some of the best known supernova remnants. It's a relatively dated plot, but I couldn't find any more recent one. The situation has not changed dramatically anyway. And so you see that in all these cases, the cutoff in the gamma ray emission can be caused mainly by either inverse Compton scattering of very high energy electrons or by inelastic proton-proton interactions with production of ions. And in all these cases, the highest energy that we could see is in the range of 10 TeV or so. Maybe there is one case with a cutoff a little bit larger, but there are other buts. Okay, so anyway, there is no evidence of any of these spectra going into range of hundreds of TeV, which is what you would expect if these sources could accelerate to PeV particles. Now, okay, let me see. So what are the questions? The question is, maybe we don't see any evidence for PeV acceleration because the supernovae simply are unable to accelerate to those energies. That's a perfectly plausible explanation. There is another possibility. Maybe we don't see it because we're not supposed to. What does that mean? Imagine a supernova. It explodes, and as you might know, the shock that is produced by the explosion is actually slowing down. And I told you in the beginning of the talk that you want fast-moving plasmas in order to create the highest electric field. So you would naively expect that a very fast shock is actually able to produce much higher maximum energies. So perhaps in the first year of the supernova evolution, the maximum energy was very high, but 100 or 1,000 years later, those particles are somewhere else. And I'll show you one instance of these situations in which this could be the case. So both of these are well-posed questions. Some are extremely difficult to address. For instance, is it impossible for a supernova to accelerate up to that energy? Hard to know because of those nonlinear processes I was talking about before. As a theorist, you have to speculate. What is the reason why the maximum energy could be 1 PeV or 10 PeV or whatever it is? And what I can safely say is that all the ways we tried have sort of failed. But I'll tell you more in a little bit. So for those of you that have never seen diffusive shock acceleration, there might be half of you or something, but just let me spend you a few seconds to say, this is the only slide with formula, but it's useful, I think, to explain why the process occurs in the first place. This is a fragment, a portion of a shock wave that has been generated, for instance, in a supernova explosion. But there are all the motions which are supersonic lead eventually to the formation of a shock drop, right? And what people do in these cases to introduce a little bit of terminology, it's a bit tricky because it's counterintuitive. So if the supernova is exploding, the shock is moving outward, but all these calculations are assuming that you are sitting on the shock. Okay, so if you're sitting on the shock, it's now the interstellar medium that is coming towards you. Okay, that's what we call the upstream. So the supernova in this approach is down here. The shock is moving this way, but you are sitting in the frame of the shock. So the interstellar medium is coming into the shock wave. And what the shock does the best, leave alone the particle acceleration, is to work as a heater. It transforms part of the kinetic energy of the plasma into internal energy. So what you do expect is that the kinetic energy of the plasma going through there, through the shock, is actually converted into a lower velocity of the plasma downstream, hotter, so higher temperature, right? So the plasma on this side is lower, but hotter. In addition to this, if you throw a particle in this system, something very cute will happen. Notice that the velocity here is u1, the velocity here is u2. So if you're sitting in the reference frame of the upstream, of the interstellar medium, then you see this part of the plasma coming towards you with a velocity u1 minus u2 with minus sign. If you're sitting in the downstream on this side, you will see the other side coming towards you exactly with the velocity u1 minus u2. So it's an extremely symmetrical situation from the point of view of a particle. If a particle is free to move and to cross the shock front and bounce on both sides, the other side will always look like it's moving towards you. And if you're able to bounce elastically on that plasma, then you change direction every time that you cross the shock, but it's like a ball hit by a ping pong player while the two ping pong players are approaching each other. The ball becomes faster and faster and faster and faster, and eventually gets fast enough to leave the system. That's the idea. The bouncing is reproduced in terms of mathematics through a diffusion equation. So this is the diffusion term. This term here is advection. It just means that the particles are carried with the plasma that is moving. And this term is the most important. It says that the energy of the particle changes every time you cross the shock by an amount which is given by the change in velocity of the plasma. You remember the electric field. So the electric field is associated with the fact that velocity is changing on the two sides. So I don't want to spend too much time on this. If you want, you can look at details a little bit later. But what people do in this case is to solve the equation separately on this side and on this side. This term is not there in those frames. So you can easily solve those equations. It's first year university courses. It's a diffusion equation in one dimension. So you can easily do that. And then the only thing you need to do is to impose the boundary condition at the border, at the shock itself. And what you get as a result is that the function f acquires a dependence on momentum, namely the particles are accelerated. And the particle acceleration reproduces a power law. And the beautiful thing that made this idea super famous is that the index of the power law, as you see, depends only on hydrodynamics. The compression factor R at the shock determines completely the power law of the accelerated particles. For a strong shock, which means that the Mach number is infinity, so it's an ideal situation, is 4. So the spectrum of the particles that are accelerated is P2 minus 3 times 4 divided by 4 minus 1, P2 minus 4. So this is a universal result. It doesn't depend on whether the shock is moving at 100 kilometers per second or 1,000 or 1,000,000 kilometers per second, provided it's a strong shock to get the P2 minus 4, which is beautiful. Of course, it's in the detail that there is a devil. Because the maximum energy that you can achieve in this system does depend on details, and especially depends on how quickly the particle can bounce back and forth across the shock wave. So how do you do that? So when is that a supernova processes most of the energy? It processes most of the energy when the shock has crossed an amount of material which is roughly the same as the ejecta, which is called the Sedov-Taylor phase. You see that all these important things have one American name and one Russian name. because all the theory was based on nuclear explosion during the 40s and 50s. And the set of Taylor phase for a typical supernova in the ISM takes a few hundred years. The time that it takes for particle to cross back and forth, it can be easily shown. I didn't do it here, but it can be easily shown to be proportional to the diffusion coefficient divided by the square of the velocity of the shock. And by equating this time scale with the set of Taylor phase, you get an estimate for the maximum energy. And you know what? It's ridiculous. It's of the order of a GeV. So this process is absolutely useless. Okay, this process is absolutely useless unless something dramatic happens at the shock that allows the particles to get back and forth much, much faster than you can estimate in this way. And that's what makes the modern theory of diffusive shock acceleration very interesting. And it's built around three stages which strongly interact with each other and make it fascinating but difficult at the same time. So the particles that are being accelerated produce a dynamical reaction on the system, namely the velocities are changed, but also produce magnetic fields in a process in processes called plasma instabilities, which are caused by the particle acceleration. This modifies the spectrum of accelerated particles in the maximum energy and feeds back in the loop here. So I'll try to give you a feeling of some of these things. The first is very easy, the dynamical reaction. Now, forget about the formula for a second, okay? And follow me with the hands, it's much easier. So you are sitting on the reference frame of the shock, and there is the ISM that is approaching you from there, right? So if you're accelerating particles, there are a lot of accelerated particles close to the shock, and while you get away from shock, less and less of these particles. So that means that the plasma element that is approaching the shock feels a pressure, and the pressure, as you know, a gradient of the pressure is a force. So while you approach the shock, there is a force exerted by cosmic rays, by accelerated particles, which is stronger when you approach the shock than far away from the shock. So that means that the plasma element is it tends to be repelled by the shock, so it slows down. So what you do expect is that the plasma, that the plasma velocity drops while approaching the shock, right? But you remember that I told you before, the spectra in DSA are completely determined by the compression factor. But that means that the compression factor very near the shock is a little bit smaller than the compression factor away from the shock. If you translate that in that formula I showed you before, it means that the spectrum of accelerated particles is steeper at low energy and it's harder at high energy. So it's not a perfect power law anymore. This was actually beautifully confirmed by particle in cell simulations, in which you see an element of fluid that is approaching and the distribution of the particles seem to slow down. At the peak of the distribution slows down. So these are thermal particles, and at the same time gets broader. So the plasma is heated up. The most important for our purposes, the most important thing to care about in terms of the maximum energy is the excitation of instability. Why is that? Again, you remember what I told you, that the main thing here is to make the time scale for particles bouncing across the shock shorter. That's what we want to do. And in order to do that, you need to somehow make magnetic perturbations much more rapid or larger. And there are three different ways that we know how to do that. One is called the resonant streaming instability. As you know, as you see with a lot of imagination, one is called non-resonant streaming instability. And then there are acoustic instabilities. That's more or less the whole zoo of stuff that we came up with. The resonant streaming instability is easy to understand, even without too much mathematics. And again, follow what I'm saying rather than the formula is easier. So imagine to have a gun that is shooting particles, the charged particles, right? So if you imagine that these particles are moving all in the same direction as a gun would do, but they are supposed to diffuse, right? That means that the beam tries to be spread, right, because of diffusion. But you think in terms of conservation of momentum, that means that there is at some stage less momentum going in this way than there was in the beginning. If you would keep waiting longer and longer, eventually the diffusion will make the distribution of the particle size drop, right? Okay, so at that point, the beam has lost all the momentum in the z direction, in the parallel direction. That's impossible. Momentum needs to go somewhere. And that already gives you a glimpse of the fact that you're actually giving that momentum to something else. And this something else is, in fact, new perturbations. So the essence of the instability is exactly this. You have a beam, the beam spreads. But while spreading, it's producing new perturbations. So the beam spreads faster. And the more it loses, the more it produces perturbation, the more the beam spreads faster. So in fact, the instability is due to the fact that the particles are diffusing. The more they diffuse, the more they diffuse. And this was beautifully shown in big simulations again. One of these things is a particle, and the wiggly part is a measure of the energy. The larger the wiggle, the larger is the energy. And what you can see here is that the shock is moving towards the right, and the particles are bouncing back and forth, but down here is magnetic field. So you see that while bouncing back and forth, the particles have actually produced a lot of perturbations ahead of the shock, thereby returning to the shock itself. In numbers, you can estimate what is the growth rate of this instability. You put some numbers in, and all of a sudden, the maximum energy that was 1 GeV in the absence of all this phenomenology has now grown to about 20 TeV. So 20 TeV for a shock of 10,000 kilometers per second is a very reasonable number, but there is no way that this can become as large as the PeV. So this instability fails in reaching the high energies that I was mentioning in the very beginning. In 2004, Tony Bell came up with another idea that is associated, it's a little bit harder to explain in qualitative ways, but not so hard. So the idea is the following, that you are accelerating its particles, so they move back and forth across the shock. Now imagine, again, one of these particles that is, okay, so there is one thing that you have to keep in mind. Scattering, namely particle diffusion, requires that there are perturbations on a scale of the Larmor radius of the particle. If you have a perturbation which has a very long wavelength compared with the Larmor gyration, it's like going on a boat, but just following the large wave. And if there are very small perturbations, then they are averaged to 0 on one gyration, so they're useless. So in fact, the only situation of interest is when the perturbations have exactly the same level of scale as the Larmor gyration. At that point, a resonance takes place in the particle direction jumps at random. So the idea here is the following. Imagine a particle that is actually bouncing back and forth across the shock, and now goes on the upstream, and there is nothing stopping it because there are no perturbations of the right wavelength. Therefore, these particles are free to move upstream, far away, right? So you lost them. But by doing so, a charged particle in motion is a current, right? And it turns out, and that's what Tony Bell showed in 2004, that if you have a plasma with a net current in the presence of a magnetic field, that situation is unstable. The tricky thing is that it produces instabilities on very short time scale, on very short length scales. So from the point of view of scattering, it's not very helpful. And here came the next step of the idea. Now you have a current, and you have all these very flickering delta B's that are flickering, and J cross B is a force. So a plasma that is sitting in that thing feels now a force which is directed which way? It's a J delta B is directed this way. So it takes rings of magnetic field and pushes them outward. It makes them bigger. So if you look at simulations of this instability, you can see that you start from these flickering things, and the structure gets broader and broader. And at some point, they become the same size of the Raman rays, and the particles start scattering. The maximum energy can be estimated in this way as well. And what happens is this. This maximum energy is a function of time. Just for simplicity, let's focus on the blue line, which is for a type 1a supernova. And you see that very, very early in the supernova history, it can reach order of several hundred of TeV. It drops in time rather quickly. And after about 10 kiloyears or so, it has dropped to about a TeV or so. Okay, so still not very close to the near region. So even in this special case, we seem to have troubles. The trouble comes mainly from the following thing. When you integrate in time the history of the acceleration from a supernova, it turns out that you can reach very high energy in the beginning, but the amount of mass that you're processing is very small. So when you transform this into energy, you see that the PV is accelerated, but it's down here somewhere. And so in the end, the spectral structure has an effective cutoff, which is not the maximum energy ever obtained in a supernova, but the maximum energy at the beginning of set of Taylor phase, which is here. So again, we're back to have maximum energies of the order of several tenths of TeV. Do we have any supernova that is currently beginning to be in the set of Taylor phase? Yes, we have supernova Cassiopeia A, which exploded 340 years ago. When you put the numbers in, it is supposed to enter the set of Taylor phase more or less now. Okay, so if there is a supernova that is at the right age, to do the damage, it would be that. And I can do a spoiler that it doesn't. So this is the maximum energy as a function of time. You see, these are just four cases because of parameters of the environment that we don't know very well. And you see that in some of them at the beginning, you have maximum energies of a couple of PV. And this is the current time. The maximum energy is supposed to be in the range of 100 TeV or so. And unfortunately, okay, so what's the point here? The point is that the maximum energy determines what are the particles that left the system and eventually are outside of the supernova. Okay, so those particles, Emax is changing in time, it's dropping in time, right? So it means that at every given time, the particles with this Emax larger than that have already left the system. So where are they? Do we have a chance of maybe seeing those, the particles that have already left the system? And in principle, the answer is yes, because this object is so young that even if moving at the speed of light, they must have covered at most 100 parsec or so around the supernova. So people, from Lasso collaboration, they tried to look at 100 parsec around the supernova. And if the PV particles are still there, they must be there unless they are superluminal. You should see that, right? So this is the field of view of the experiment, roughly. And there are several clouds of material in there. And the particles are trying to propagate in that medium. It doesn't matter how, right? Because if even if they are diffusing, it just means that they have covered a smaller distance. They're going ballistic, they just went C times T. But in both cases, the volume is already larger than the volume observed by Lasso is already larger than the distance traveled. And these are the spectra that we expect to see from from that area. And these are the upper limits of the experiment. And as you see, they are already borderline. So even if high energy particles were accelerated there, we would have seen them. So it looks like it's pretty much ruled out that this object is accelerating or has accelerated enough very high energy particles at any time in the supernova. We actually see gamma rays not from the region, not only from the region around, but we don't from the region around, we put upper limits, but we actually see gamma rays from the source itself. This is gamma ray emission from Casset, and you see that the maximum energy right now in gamma rays looks to be around a few TeV, which means if it is PP scattering, about 10 times as much. So again, 20 TeV. So bad news, so, or whatever. I mean, not bad news, what nature is doing. So given the difficulty in accelerating cosmic rays up to the knee in supernova remnants, the question, of course, is legitimate. Is there any other option? After all, we came up with supernovae based mainly on two ingredients. One is the energetics, and two, that we see no thermal emission from the object. But they fail to reach the maximum energy that we observe. So is there any option? Well, for sure, we see very high energy gamma rays from pulsar wind nebulae. Problem is that we know for sure that those gamma rays are coming from electron-positron pairs. So they have nothing to do with protons. And in fact, we can actually put strong limits on how many protons there are in pulsar wind nebulae. And there are, not enough at all to associate them to cosmic rays, to hadronic cosmic rays. There are selected star clusters. Maybe I can say a few words about this. And in one of them, in Cygnus region, gamma rays up to 2.5 PeV have been observed. Gamma rays, not cosmic rays, which means that in cosmic rays, you have at least 25 PeV somewhere. And third, there are a few microquasars in which the gamma ray spectrum looks like straight up to 100 TeV with no evidence of cutoffs, which again might suggest that those regions are more prominent, they're more promising. So a few words about star clusters. So for those of you that don't know, star cluster is simply a collection of young stars in a very small region, typically of the order of a parsec or so. And you have 1,000 stars in that region. These are young stars, so most of them are actually ejecting large amount of material with typical mass loss rate of the order of 10⁻⁴, 10⁻⁵ solar masses per year. But since they are so close, you don't really see the individual winds. They merge into a collective wind, which exerts a pressure in the surrounding medium. So actually the ISM in which the object is formed it's plowed away, and what happens is you have a forward shock and the reverse shock structure, which eventually reaches some sort of quasi-stationary situation. So you have a forward shock up here, which by now is typically in the range of 10 kilometers per second. So it's a very, very weak shock and significant. And then you have a termination shock, which is just very strong because the winds are moving at a few thousand kilometers per second from out here, from in here. Now, if you remember when I talked about DSA in supernova remnants, I told you that the main problem was in actually inhibiting the fact that particles would leave upstream. That's the main thing that you want to avoid. Particles need to go back to the shock. The beautiful thing about this picture is that the upstream is in here. The upstream of the termination shock is this region here. So the particles cannot leave from the upstream. They must go back to the shock. So from that point, it's a good news. Now, we have run many calculations since our paper in 2021, but in none of these calculations, you can actually reach really these very high energies that Lasso is observing. But even even worse than that, actually the fit to the data of Lasso that Lasso and Ock that we have achieved requires extremely severe assumptions on the system, assumptions that I wouldn't have usually adopted in my wildest dreams. So I would say that so far it's not very clear what is happening there. Now, the very high energy particles, these very high energy gamma rays, we suspect that they are actually galactic cosmic rays that are scattering against the dense cloud of material which is outside. So it's not really particles accelerated in the star cluster, but are rather cosmic rays that are interacting while impinging on the cloud from which the star cluster was formed. But this is something that is being studied very actively in the last few years. The other possibility is these microquasars. Microquasars are basically binary systems of a massive star and a compact object, either a black hole or a neutron star. And usually the compact object accretes matter from the rush lobe of the other star, and most likely forms an accretion disk and sometimes a jetted structure emanated from the black hole. In some cases, really a few cases, we have evidence of super Eddington accretion, so that the luminosity all of a sudden jumps to above 10 to 39 Hertz per second. And you remember from the second or third slide I showed you, Emax equal to square root of L is normalized 10 to 39 Hertz per second. So if you put 10 to 39 Hertz per second in that formula, you get of the order of 100 eV for the maximum energy. But I also told you that that is absolute upper limit. It doesn't mean that you actually do that. So what is that we know? That's what I just told you. So in principle, these sources could be effective accelerators. But what do we see? Well, this is probably the case that we know the best. And I love this picture because look at this. These are two separate objects. This is the microquasar in here. These are the points where the jet is hitting something. And so this is the reverse shock of the jet. And this is the material slowed down after you don't see the jet, you see? So the jet actually is seen in the radio in this very inner region here, then it seems to disappear. We don't know exactly what happened. And then all of a sudden it reappears at about 50 parsec distance, hits something, and the material is slowed down, and that's the X-ray emission from behind the shock. And then there is this huge thing here. This is the remnant, the supernova remnant, that is associated with the explosion that caused the black hole in the microquasar before. So here there is a black hole in here somewhere, and it was caused by the explosion of a supernova, and this is the supernova in question. And these elongated things are supposed to be the effect of the jet impinging on that system and blowing a bubble into those things. This is the microquasar SS433. And it's the only case really in which we actually measure not only the spectrum of the gamma rays. As you see, it extends to about 100 TeV without evidence for any suppression. This is the good news. The bad news is that we see the morphology. The good news is that we see the morphology. The bad news too, because from the morphology, we see that the emission in gamma rays decreases in size with the energy of the particles, with the energy of the gamma rays. Do you know what that means? Well, it means that we are seeing emission from particles that are losing energy very quickly. And that won't happen for protons, but it happens for electrons. So we're sure that at least in this case, the emission we are seeing is inverse Compton scattering of very high energy electrons. So paradoxically, if we found another source of PV electrons, as also in nebulae are, but still no trace of the associated protons. So in this case, it doesn't mean that there are no protons accelerated. They could be, but there is no signature whatsoever that they're there so far. There is another instance. By the way, it was also observed with LASO. And you see that there seem to be sort of two components. This is the component that was already seen by Hess and seems to be fit well with the maximum energy of the electrons in several hundred TeV of energy. And this would be inverse Compton scattering. Then there are these data points which extend to very high energy. And it is speculated that perhaps it could be an additional component. We don't know really. They seem to correlate more with the central region, not where the jets are. Does that mean, what does that mean? Well, it could mean that the particle acceleration is taking place both at the jets and in the inner engine. Could be that the black hole magnetosphere is accelerating the particles. It turns out also that there is a cloud of gas which spatially seems to be overlapped with that region. So it would be a mild suggestion that perhaps we're seeing protons hitting on a gas target and producing these gamma rays. We don't know for sure. So for now, this is all what we know. I just want to stress again that you see this spectrum here that rises. This is multiplied by square. That means that the spectrum of the protons, in order to do that, would be very big. So it's not shock acceleration. If it is protons, it must be something else. Reconnection, perhaps, or other processes perhaps occurring in the central part. There is another object, a V4641 Sagittarius. Also in this case, gamma ray emission is observed from a very large region around the microquasar, and it extends to very high energies. And these are this is a collection of spectra from Hess, from Ock here, and from Lasso here. You see, it does extend almost to, say, 500 TeV or so, but the peak emission is, again, around here, which is 20, 30 TeV. The spectra don't look anything like protons, honestly. So it is very difficult to speculate that here cosmic rays are being accelerated. Maybe, perhaps we're again looking at an electron accelerator, a lepton accelerator rather than a proton source. It is definitely interesting, right? I mean, whenever you do see gamma ray emission extending to these high energies, you know for sure that the parent proton, of course, must have had an energy larger than that. So clearly there are particles accelerated up to PeVs, but we don't know if they have anything to do with the cosmic rays that we see at the Earth as cosmic rays at the knee. So I'll, well, perhaps I will just leave it here and perhaps accept questions on the topics. Please shoot on everything that I said. Okay, thank you.
Questions?
Is it related to the abundance of the subject? Anything with the spectra that you have, just not need to reduce that the photons at the base of the sheet, but you need enough of those. So all of these candidates are cosmologically relevant to reduce the photonic spectrum that you were showing at the beginning, or are more a source more likely to be responsible for them?
Right. So first of all, cosmologically, no. This is all
yeah,
yeah. So this is all galactic stuff. Energetically speaking, that's a very good question. So supernova remnants are for sure way more than enough. Okay. At least in the GeV range. In the high energy regime, in the high energy range, they run out of steam and they cannot get up there. Now, what about the others? For star clusters, the energetic is very similar for supernova remnants for obvious reasons. I mean, after all, those stars will explode as supernova remnants eventually. So the energetic within a factor of 2 is the same. For microquasars, the energetic, it's much more flaky, right? Because we need to assume something on how what's the frequency of formation of a binary system that ends up being a microquasar. How quickly and for how long it becomes a superheated source, because this is irrelevant for the energetic, but it's important for maximum energy, right? So only during the phases in which it goes superheated that you reach these very high energies. It's difficult to have constraints on these. Each microquasar that we study seems to have somewhat of its own history. So we don't have a luminosity function, right? Now, this said, however, we tried to assume some reasonable parameters, which means assuming that you form these things one every 1,000 years or so, one of these microquasars, and that they remain active for about 10 to 4, 10 to 5 years. And doing that, you basically are at with an efficiency of 10%, you are at the level of the data in the rays that can be. These preliminary results that we're doing, the calculations we're doing, I'm doing it with a student, Chun Kai Wu, and they seem to point to a large anisotropy though of cosmic rays for obvious reasons, right? They are very rare. So if you build at random a realization of the galaxy, there will be realizations in which you have none of them, and some in which there is one, some in which you have two, but not a half, not 100. And mostly out of the galactic plane. So you would expect anisotropy pointing in some direction, which might have something to do with that. But for to answer your question, original question, energetically speaking, all of the three in the region of the knee seem to work. The first two have problems reaching the knee in terms of maximum energy.
So I have a couple of questions. The first one is on the supernova, on the Cascade case. So you mentioned that theoretically, at least the model can, in principle, produce something that reach PV or more, and that the observations rule out this possibility. So the question is, from what we understand from this calculation, and from the comparison with observation, what's wrong in your opinion, the physics that is putting this calculation?
Nothing.
So why
So,
you want to put this?
No, that's probably I went too fast on that. So let's take the most optimistic case here, which is this, either case 2 or case 4. Again, it's just case 3, 4, 2, 1, 3, 4 means that we changed slightly the m dot of the pre-supernova star. So how much wind it was producing. So you remember this is a type 1b supernova. So it had a red giant wind preceding the explosion, typically with a 10 to minus 5 solar masses per year, velocity of the order of 10 to 20 kilometers per second. But again, you have to change it. We don't know for sure. So you have to change these parameters a little bit. And this is the fluctuation in the results that you get. So here you see that about months after the explosion, you can reach energy of the order of 1.5 PeV. When you do the convolution in time, remember again, this explosion in a wind, right? So the density profile of the wind goes like 1/r squared. And the set of Taylor phase is reached 300 years later. So this is a lot of energy, but it's involving a very small amount of mass. So there is no contradiction with the data in the sense that, let me show this first. So this is the spectrum of the cosmic rays that were released into the interstellar medium in case 4. You see that 1.5 10 to 6 is down here. The peak is around here, which is 100 TeV, right? So even this scenario is currently borderline with the data. This was case 4, it's up here. See, it's already exceeding the limits. It doesn't mean, you see that 1.5 10 to 6 is up here. There is nothing left. Okay, so there is no contradiction in the sense that you do reach those energies, but in terms of integral over time, they count for nothing. So in order for the maximum energy to be seen in the spectra, you need to reach those maximum energies at the beginning of set of Taylor phase. Otherwise, they are lost. That's the thing that throws most of this in the garbage. The idea works beautifully, but the maximum energy is high when the shock is so fast, but it's processing very little mass. Now, to be fair, I mentioned to you before that there are 3 things that we thought about to amplify the magnetic field, but I only discussed 2 of them. The reason being that this third is even more of a nightmare, in the sense that, what is the idea? The idea is that perhaps the interstellar medium, but for sure we know that the interstellar medium is not homogeneous. It has homogeneities. Okay, so again, follow me with the hands. You are in a shock wave, in the reference frame of the shock wave, and there are more cosmic rays next to you than there are far away. So there is a gradient in the cosmic ray pressure. A gradient is a force, right? So if you have inhomogeneities which approach the system, they feel a force that under certain conditions can produce eddies. So if those inhomogeneities can turn into something spiraling. And if so, if that happens, then the magnetic field there can grow through a process that is usually referred to as kinetic dynamo. Yesterday night, my postdoc sent me the results of some MHD simulations of this. I'm not ready to show them because there are still things that we don't understand. But there does seem to be a very strong magnetic field amplification. We are not sure that it happens on the right scales yet. So the reason why I decided to not discuss this is that there isn't enough grounds to actually reach some solid conclusions yet. But I want to remind you what I said before. I mean, this is in the realm of the first question, right? So the first question is, do we not see the PV because they cannot accelerate to such energy? But it's a theoretical question, right? I don't know. It depends on so maybe some of those instabilities I understood nothing about. And maybe they are so effective that now all of a sudden the maximum energy can be much higher. The problem I see is in the second point, namely in those few cases in which if there was something much more effective, I would have seen it. I see exactly what I'm expected to see based on the first 2 of the instabilities, on the instabilities that I know about. Okay, so I'm not much too worried about my ignorance from the theory part. I'm more worried about the observations of what we do know. And those seem to be sufficient to say that, at least for the cases that we have been able to study, in those supernova remnants, there is no trace of PV. Again, it might be a bias. Perhaps there are many more in which there is, and we're not aware of. But to the extent that we base our knowledge to the things that we do observe, I would conclude that supernova remnants are hard to imagine as sources of PV.
I think we can stop here. It's very late. You can ask questions offline. Thank you again.
Ti faccio vedere una cosa che